Japan is a nation perpetually shaped by its intense seismic activity. Positioned on the Pacific Ring of Fire, it experiences thousands of earthquakes annually, ranging from minor tremors to powerful destructive events. This geological reality has profoundly influenced its civilization and technological development. This enduring challenge has propelled Japan to become a global leader in seismic engineering. Its unwavering commitment to mitigating earthquake risks has driven decades of innovation. The nation's expertise is sought after worldwide, setting benchmarks for resilient infrastructure. Japanese cities are not merely built, but are intricately designed to withstand devastating earthquake forces. Every skyscraper, bridge, and essential utility is conceived with seismic resistance as a fundamental priority. This proactive approach distinguishes Japan's urban development. Our focus today is on the complex systems and inherent trade-offs involved in achieving this resilience. We will examine the advanced engineering principles and societal preparations that underpin Japan's earthquake-resistant urban environments. Understanding these aspects reveals the intricate balance between safety, cost, and innovation. The bedrock of Japan's seismic resilience lies in its choice of building materials and structural design. Reinforced concrete and high-strength steel are primary materials in modern construction. These composite materials offer superior performance under dynamic loads. Reinforced concrete provides compressive strength and stiffness, while steel rebar enhances tensile strength and ductility. This combination enables structures to endure significant deformations without catastrophic failure. These materials are crucial for absorbing and dissipating seismic energy. The inherent properties of these materials allow buildings to move flexibly during an earthquake. They are designed to sway rather than rigidly resist forces, distributing stress throughout the structure. This engineered flexibility is a cornerstone of seismic safety. Base isolation technology represents a crucial advancement in decoupling buildings from the ground's seismic motion. This innovative system inserts flexible layers between a building's foundation and its superstructure. It fundamentally alters how seismic forces are transmitted. These isolation layers typically utilize a combination of laminated rubber bearings, steel plates, and sometimes viscous dampers. The specific composition is carefully engineered to suit the building's characteristics and the expected seismic profile of the site. These components work in concert to provide both flexibility and stability. The primary function of base isolation is to allow the building to move independently of the ground's shaking. As the ground shifts violently, the isolation system absorbs the energy and extends the building's natural period of vibration. This significantly reduces the acceleration forces experienced by the structure above. By lengthening the building's vibrational period, base isolation dramatically lessens the earthquake impact on the superstructure. It protects both the building's integrity and its internal contents, minimizing damage and ensuring greater safety for occupants. This technology is a hallmark of high-rise construction in seismic zones. Beyond base isolation, damping systems act as vital shock absorbers within the building itself. These devices are strategically integrated into a structure to dissipate energy generated by seismic activity. They are crucial for controlling motion and reducing stress on structural elements. Dampers operate by converting kinetic energy from the building's movement into heat or other forms of energy. Common types include viscous dampers, similar to automobile shock absorbers, and tuned mass dampers, which counteract resonant frequencies. Their application is tailored to the building's specific dynamic characteristics. These systems minimize building movement during tremors, particularly the amplitude of oscillations. By actively resisting sway, dampers reduce the forces transferred to columns, beams, and shear walls. This prevents excessive deformation and fatigue in the structural frame. Damping systems are critical for reducing damage to both structural and non-structural components. They also significantly enhance the safety and comfort of occupants during an earthquake. Their inclusion underscores a holistic approach to seismic design, protecting the entire building system. Effective earthquake preparedness extends beyond a building's primary structure to its internal infrastructure. Flexible piping and fixtures are integral components within buildings designed for seismic resistance. This engineering accounts for anticipated building movement during tremors. Pipes, conduits, and utility lines are installed with flexible joints and seismic loops. These allowances prevent rupture or disconnection when the building sways or shifts. This design avoids rigid connections that would otherwise fail under stress. The goal is to withstand significant movement without breaking or causing secondary hazards. For instance, maintaining the integrity of gas lines prevents explosions and fires, while intact water lines reduce flooding. These considerations are vital for overall safety and recovery. Complementing robust engineering, public preparedness, and education are cornerstones of Japan's earthquake resilience strategy. Regular drills are conducted in schools, workplaces, and communities, simulating various earthquake scenarios. These exercises instill crucial response behaviors. These extensive public education campaigns are essential for informing people on how to react effectively during an event. They cover topics such as drop, cover, and hold on, evacuation routes, and emergency supply kits. Knowledge empowers individuals to make critical decisions under pressure. Such widespread awareness and practice are crucial for minimizing casualties and ensuring public safety. A well-informed populace can act quickly and appropriately, reducing panic and facilitating organized responses. Education transforms fear into proactive readiness. Implementing advanced seismic engineering entails significant financial costs and design constraints. The sophisticated materials, technologies, and rigorous testing contribute substantially to overall project budgets. These expenses are often absorbed through various mechanisms. Stringent building codes in Japan necessitate higher construction expenses compared to regions with less seismic activity. Compliance requires specialized labor, additional materials, and advanced analytical modeling. These requirements elevate the baseline cost of development. These increased costs and design requirements can impact housing affordability and design flexibility. Developers must balance architectural vision with strict safety mandates, potentially leading to higher property values. The premium for safety is a constant consideration in the urban landscape. Despite remarkable advancements, even the most advanced earthquake-resistant technologies are not foolproof. No engineering solution can guarantee absolute immunity from the forces of extreme natural disasters. There are inherent limits to what current technology can achieve. Earthquake-resistant buildings can still sustain damage, particularly during exceptionally powerful or long-duration seismic events. The objective is damage control and life preservation, not absolute indestructibility. Minor to moderate damage is often an acceptable outcome. The primary goal remains to prevent catastrophic collapse and protect lives. Engineers strive to ensure occupants can safely evacuate, even if the building is rendered uninhabitable post-event. Eliminating all damage is generally neither feasible nor economically viable. Seismic engineering is a field characterized by constant evolution and innovation. Researchers and engineers continuously develop new technologies and refine existing ones. This ongoing process is driven by lessons learned from past earthquakes and advancements in material science. New seismic dampening systems, smart materials, and advanced analytical modeling techniques are perpetually under investigation. Collaborations between academia, industry, and government agencies fuel this progressive trajectory. The pursuit of enhanced resilience is ceaseless. This continuous process of learning and adaptation ensures that Japan's infrastructure remains at the forefront of earthquake safety. Each major seismic event provides invaluable data for further research and improvement. It is a testament to persistent scientific inquiry and practical application. A significant challenge in Japan involves the integration of modern seismic technology with existing cultural heritage structures. Preserving historical buildings while enhancing their earthquake resistance requires innovative and sensitive engineering solutions. This often involves discrete retrofitting. Balancing aesthetics, cultural heritage, and modern safety standards is a complex undertaking. Traditional wooden structures, for example, possess inherent flexibility but may require additional reinforcement. Engineers must respect original designs while introducing new elements. This represents a constant negotiation between the past and the future of Japan's built environment. Solutions often blend traditional craftsmanship with cutting-edge materials and techniques. The goal is to safeguard history against future seismic events. For residents of Japan, daily lives are subtly but profoundly shaped by these extensive seismic safety measures. The pervasive presence of earthquake-resistant design is an unseen layer within the urban fabric. It provides a baseline of security in a tectonically active region. There is a constant, though often subconscious, awareness of potential seismic activity. This permeates public consciousness, influencing personal preparedness and community planning. It becomes an intrinsic part of the societal contract. This awareness influences everything from individual household emergency kits to national building codes and urban planning strategies. The collective memory of past disasters fuels a continuous cycle of vigilance and improvement. It is an ingrained aspect of Japanese life. Despite advanced building designs, these systems may not prevent all forms of disruption following a major earthquake. While structures might remain intact, vital lifelines can still be severely impacted. The resilience of the built environment does not guarantee uninterrupted functionality. Power outages, water supply disruptions, and transport delays are common consequences of significant seismic events. These disruptions can paralyze economic activity and severely impact daily life. Rebuilding these networks often takes considerable time. Earthquakes can still cause significant economic losses, even with resilient infrastructure. Business interruption, supply chain disruptions, and the cost of repair, even for non-structural damage, accumulate substantially. The societal cost extends beyond direct structural damage. The long-term implications of Japan's seismic focus extend to its urban planning and broader infrastructure development. City layouts, transportation networks, and even land use policies are influenced by earthquake risk assessment. This shapes the very geography of urban spaces. This constant adaptation to seismic forces shapes the cultural landscape and creates a unique environment. It fosters a culture of innovation, meticulous planning, and collective responsibility. The Japanese approach becomes a model for other at-risk nations. The emphasis on resilience is reflected not just in physical structures, but also in the societal mindset. It underscores a deep respect for the power of nature and a persistent determination to coexist safely with it. This forms a distinctive aspect of Japan's identity. The assumption that Japan has somehow conquered earthquakes is ultimately misleading. While advancements are profound, the geological forces at play remain immensely powerful. No nation can fully eliminate the threat posed by seismic activity. The reality is a complex, constant balancing act of risk, innovation, and societal priorities. Japan continuously invests in research and infrastructure, but every decision involves trade-offs. This ongoing process reflects a dynamic interplay between human ingenuity and natural forces. Japan's approach to seismic engineering is undoubtedly a remarkable achievement, setting global standards for resilience. The dedication to protecting lives and infrastructure is unparalleled. This commitment serves as an inspiration for other earthquake-prone regions. Ultimately, it is a testament to human resilience, ingenuity, and continuous adaptation to nature's formidable forces. The capacity to learn from disaster and proactively build a safer future defines Japan's strategy. This enduring effort shapes its future. It serves as a powerful reminder that even the most advanced technologies have inherent limitations in a constantly shifting and unpredictable world. Absolute control over natural phenomena remains beyond human grasp. Prudent coexistence is the ultimate objective.